Yes, is it visible?
Yes, it's visible, sir, now.
Okay.
It's visible
So
and
good.
readable.
Okay. So good morning to everyone. And after this wonderful session by Dr. Satakshi on linear algebra, which is one of the backbone of this all data science and machine learning, because if the three things are important in any algorithm which we work in machine learning and data science, so you need the fundamentals of linear algebra, one of the important part, and statistics and optimization. So three things basically is what you can understand as the whole package of this data science and machine learning. So one of the backbone and wonderfully explained session last 1 hour, and this will help you in all to understand so much the buzzword you talk about the deep learning to machine any algorithms. You will feel that the matrices are in place where we are operating with that, and we are getting some many applications in a different domain. So after that wonderful session, so now I will try to be more superficial part now rather than more fundamental parts, where I will talk about this knowledge transformation and application in different problems where you can think out to apply, including natural language processing to the computer vision. So what you will get in my talk in the next 1.5 hours, initially I will talk about some 5 to 10 slides about quick machine learning introduction. And then I will talk about the need of this, why the transfer learning. And then some application I will discuss, and I hope that it will be helpful to you who are going to apply in a different domain. But again, to understand each and every fundamentals, you have to have the knowledge of linear algebra and statistics and optimization. But to apply, nowadays many packages are available on TensorFlow to PyTorch to everywhere where you can play with that. So might have many of you have done that sort of transfer learning applications also. But in this whole session, I will try to connect again. And in between, anytime if you have any question, you just stop me and you can discuss. So don't wait. If you have a question, raise your hand and ask the questions. I will try to respond at that time. If you write on the chat box, then possibly at the last, I will read that and then I will respond. So let's talk about let's start this, and first I will move to that, the machine learning part. Everyone is talking about the machine learning. And this learning is not different, or you can say that some similarity you can draw from the human learning. It's not as a human what we can think. What we understand, we try to make the system in that way, or our imagination comes out something different, and then we try to build up that model. So in general, what is this machine learning is? A learning process, which you can say the way back definition given by the Simon. Any process by which a system improves performance from experience. And that's what the learning for the human also. You can draw this definition for, it's not for the machine only. What is a learning for any person, any individual human being? If you are seeing the kid, let's see this picture. I used to keep this small robot where we are talking about this robot to teach, learn, but at the same time, that's what we do day-to-day life to teach this kid also. Many things we do that. Many vision problem, many NLP problem, many cognitive problem. You may visualize that how this kid is learning day-to-day activity. And then how the same thing, the learning, not exactly, but up to certain level we can make for a robot or machine to learn. So what we do in the machine learning basically for the learning task, for a given data set, we evaluate that, or we see that this performance of that model with the experience is improving or not. We measure that improvement. And then we say that if it is improving, that then we say that learning is happening. So even in any computer program, what is this machine learning? It's a functional form, you can say, or in a machine learning program or computer program, you can say to learn from the experience. Experience here is the data set. with respect to some class of task. What is the task that is important? What is the objective? What is the goal? And accordingly, we learn. And same thing happened in the machine learning models. Any program which you can say with certain target for a given data set, how this performance is improving or how this performance is better than the previous without data set. And we measure this performance. And if this performance improve, then we can say, okay, this machine learning, something learning is happening. So data set is very, very important. You might have heard this term in the data science or data analytics. The data is the oil, new economy, data is the oil. And very, very important part. You might have observed that, I will talk about this all online platform of, you can say, shopping, either Amazon and Flipkart. What is happening now? They are tracking, they have the model, and they are tracking your behavior, because in general, every individual within a home have a mobile phone and may have their own Amazon account. So each one, they are tracking what you are buying on that. So the data set they are gathering in the back side. And the same kind of data someone else also using same behavior, so sometimes they map that data for you also. Even though for your individual case, what is happening as the time passed for last 4 to 5 years, historically they have measured data sets and then they try to understand, or somehow they are up to certain level, they are right what you are going to buy once you are going to surf on the Amazon platform, and they predict accordingly. They understand that what kind of things you are seeing that and what range of price, and accordingly they, instead of showing everything, they prioritize and show you. So just imagine down the line for any kid, a 10-year or now young generation, a lot of time they are giving on this online platform. You just imagine down the line of 20 years what will happen. With the data set, their learning model will improve, accuracy will be high, and then what? They will understand that, okay, how the things are happening, and they learn that your behavior, and accordingly this. And it is not only the online platform, nowadays in everywhere, the models are enriching their experience and knowledge, their capability, their capabilities are increasing with the data sets. A very, very important part, this machine learning. And though I will not go in detail each and every term of machine learning, but quickly next 5 minutes, different approaches on this machine learning, I will try to just summarize. So in the machine learning, there are many kind of algorithms are there. It depends on what kind of data sets we have. One is supervised learning. You understand that this phenomena that the school teaching, what you can say, or any, where teachers taught, give the question, ask same kind of question in the exams, and then they measure that how the kids have learned the things. So in this case, one supervisor or some labels are available. What happened whenever a data sets you have, and for a data set, apart from feature, if the label of the feature means the category of that data sets are available, then you can say that it's a supervised learning problem where data sets and corresponding labels are available. What it means, and in your mobile phone, huge number of images are there, and if for each image you are storing that how many persons are who are there in that, so you are tagging that. If tags are available, then you can say the data sets are labeled one, and we need a supervised learning algorithm. Within that supervised learning, again, it may be a regression problem or it may be a classification problem. What is the difference with that? In the classification problem, so that labels are discrete, means more than one, and in the regression problem, these labels are continuous. So again, further within the classification, many algorithms, including you can say you can use either logistic regression, support vector machine, ANN, and there are so many. And many huge applications you can say any diagnostic where you want to solve, you may go with this. If the labels are available, you can go with that classification algorithms. You can identify a fraud detection in a different application, either banking or credit card. You can see that image classification. If you are doing that, it's image of cat or image of dog, and if you have a label data previously to train the model, then it comes within that category. Supervised learning for the classification, many huge applications, and you just Google it and many applications you can see that. Within the regression category, again, you can see that within the supervised and regression I'm talking about, you may think about the time series data where you want to predict the share market value. You want to predict the weather forecast. That case also comes out within that category. Estimating the life expectancy. Any product, any industry is just making that. So what will be the life of that product? Apart from the human, the life of any product. If you want to predict, looking at the data sets and features, you may model your problem as a regression problem, and then including to least square, to logistic, any least square method, to any either support vector regression if you want to use, or NN for this task also, you can play with that and you can solve this problem. So this whole, so many applications you can see for supervised learning. Same way, just a minute. Okay. In unsupervised learning, and this is the buzzword nowadays, what happened? This is the one of the challenges, that most of the data sets which we store is unlabeled. In the supervised category, many work so many years have been done, and the people have achieved in a different problem up to 90-95% accuracy in a different applications. But in the unsupervised, where every time data sets are there without the label, even if you see, we all nowadays are using this mobile phone to capture the images, and every day might be 5 to 10 images we are, or anyone is capturing. Are you labeling that? Are you giving the tag who is there in that image? No. You know that, but others may not. As a person, others may say that this is a man or woman, but they cannot tell that it's a capturing image or someone else until he or she is knowing that. So most of the time, we capture the data, but we keep it as unlabeled. Even if you see and talk about this satellite imaging and all, huge data sets are coming up, but tagging labels for those data sets or not, or if it is there, it's very, very few. Very few labels or tags are available. Most of the data sets are unlabeled. If you go and satellite data and do this labeling, it's very, very time consuming. It's not so easy in a minute you can do that. You need an effort, you need experts to tell that. So this is a new real challenge problem. Most of the data sets are unsupervised or unlabeled. Then how we can make the learning and how we can utilize those data sets. So there are huge development in that category in the last 2-3 years, even though it is old problem, but new algorithms are coming to take up this unsupervised to semi-supervised to transfer learning, and that's zero sort and few sort way, which I will introduce in the coming slides. So within that unsupervised, you can say what, even that it could be a dimensional reduction where no need the labels, you just understand the feature properties. And one of the application of this linear algebra, this eigenvalue and eigenvector, you can say that for the dimensionality reduction. And if you know the part of this PCA, principal component analysis, which is basically based on that. So feature engineering, you can say that where labels no need, the data sets we want to understand. And in that, many big data visualization is one of the important part in data science. How to visualize the data, and if to visualize it, the hard dimensions are there, it's not so easy. But PCA and other algorithms are very, very helpful in that way to visualize, and you may see that many huge applications in that domain. Then structural discovery, meaningful comparisons, and then you can see this. Even supervised and unsupervised category, you can see that there are class update algorithms where which are discriminative models, which are nature is discriminative, means if you want to classify the data, what do you do that? We look at the labels, and according to the label, we try to draw a plane, hyperplane, or any polynomial so that I can classify that the data sets. So such kind of models are discriminative models. But some models are relying on not on only the labels, they're relying on the feature distribution. And they try to learn the distribution, what kind of data sets are. And within that category, it comes out generative modeling. Either you understand the Bayesian classifier and Bayesian network, or also you can say within that category. Even in that unsupervised classification problem, in the clustering, you can see that what we do that in the cluster, and then we try to make that many applications in customer segmentation, target marketing, or recommendation system. Within that category also, it could be a k-mean or it could be Gaussian mixture too, where we try to fit the distribution rather than only that k-mean only. There are different kind of algorithms which you can see that where we are focused on learning the distribution of the data, or just seeing that data sets and mean and variance, and then accordingly you play. So accordingly you may fit a different algorithms. So third category, which within that is reinforcement learning, and you can see this application in basically many games in the AI when learning tasks are needed. Real-time decision, if you want to do that. So in the real-time decision, you can see that huge reinforcement learning applications, because in the real time, many things comes out from the many dimensions, and you have to take sequentially decision making. And in that decision making, the previous knowledge we want to use. And in that category, apart from the robotics application or in game, you can see the huge work with the application of reinforcement learning. In the broader category, there are many things also comes out. This is what ML is. And data science, which Java data and different kind of data sets which we have to look at what we want to do with that data. What is our target? What is our objective? What kind of data sets are available? And accordingly, we can pick our algorithms to work with that for that. Though in two things, though I will not go each and every algorithms, two things are important whenever we do that. This machine learning. First one is that already way back the statistics are there. So what is there in the machine learning? Why we are talking about the machine learning? If there is already so, because least square method is a part of linear algebra. Sometimes people say that statistics. Why this one is the machine learning? Why in machine learning we study this again? The one you can say that the important part, what it differs this machine learning, or you can say compared to exactly the statistics, is that here we more focus on generalization. Generalization means what happened if you look at this school teaching, not necessarily that those who are, what happened in general as a teacher, what we do, we taught something, we asked the questions, and in the exam almost same kind of questions are little bit variations, and then we grade the students some grade, either 9, 8, 10, whatever it comes out. But suddenly for placement, suppose for placement, a company comes and some ask the question maybe related to the same domain, but in that case, not necessarily that a topper of the class, or like 9-pointer or 10-pointer of a class only, or he or she is first going to solve that open problem. Not necessary, anyone can. sometimes. So what I'm trying to say, within the statistics, without generalization, where focus is, if a data set is there, you choose what statistics will be in that case. The topper is A, 9.99 with this value, mean is this, variance is this. What machine learning say? Okay, there are certain training purpose that people have a topper and this one have a different test problem. It may be not exactly same, but might not have been discussed in the classroom. And I will see the performance of those guys with the new data sets. And if performance is good, then I will choose that model. So what training model is saying, only training model, if you're relying, that you can say is this statistically fine. But the testing model, sometimes what happens, those person who are good in the training may not be good in the testing. So this comes out overfitting phenomena, or you can say actually spoon feeding case. You're too much tuned up and trained for the training purpose, but suddenly new problems comes out that are flattened, not able to solve. So this is the overfitting phenomenon. And sometimes those who are poor, very poor in the class performance, even then how they will do in the test case. In that category, chances are random, very less. So not trained at all. So not trained at all is no guarantee for success. But trained perfectly, then you will solve the real problem. It may or it may not. So what machine learning is, make a balance between underfit and overfit. Choose a model which perform good during the training as well as testing. Not good only the training and bad in the testing. It is overfit. Training poor, underfit. So the whole machine learning idea is to generalize a model which performs better during the testing part. How we do that? Simple concept. If you have an underfit model and performance during the training is poor, it means model complex, power of model is very weak. Increase the model complexity in that case. Model complexity, you just increase if it is underfit and then try to fit. Otherwise, other case, if you are using overfit phenomena, then in that case, we do the regularization. So two important part, if underfit, increase the model complexity. If overfit, do the regularization. And then get the model which performs. So this is the very, very important, this trade-off in every machine learning algorithms or deep learning, whichever you are going to apply. This concept is very, very important, and that's what we do in any simulation. After that, the analysis, either F1 score or depending on the different kind of analysis, we do it. Okay. So three things are important in every ML and DL. One, representation means what kind of model you want to choose, then how to optimize, and then how to evaluate, how we measure that. So three things are very, very important in every ML and DL algorithms in a nutshell. Though why this buzzword, the difference between ML and DL, what is that? You might be knowing that quickly. In machine learning, initially, before you can say 2005, 6 or 10, basically after that huge success of deep learning comes out, 2010. Before that, people talk too much. Even today also they are doing. We talk more about the feature engineering. What was that? And we say that this model performance will be better. This model could be any SVM or any model if our extracted feature are nice. And who will extract the feature? You need an expert or you need a PCA kind of algorithms, a lot of stuffs are there. So in the machine learning, a data sets comes. We do some feature engineering so that we can extract the important features. Then we apply your models and then we classify. So anytime if this feature extraction is poor, your model performs badly. So that later on people say that this feature extraction engineering is so much affecting the model performance. So can we do something so that this extraction also comes out within that? So what happens? Then feature extraction, this person or expert who were doing that, was now merged in the deep learning. Okay, this feature extraction also I will do in the network. You talk about the deep learning, CNN, and whatever the model. And then people say, oh, so easy. Just give me input, I will get output. The deep learning, what we do that. And huge success in last 20 years. You are saying everyone is talking about the deep learning. Okay. But nothing is free. People say that, okay, this feature engineering no use, and I have a powerful method who is giving better result than this expert, and I'm beating this all machine learning models in terms of numerical. But what I said, that nothing is free, no free lunch. What happens with this, the deep learning models, lot of structure comes out, or many powerful things people are doing, but at the same time issue comes out that how to explain. Here at least there were some features which we were knowing that, and then we were able to somehow explain that why this output is coming up to certain extent. But in the deep learning, it becomes very, very difficult to explain why this output is coming. And this is now the open problem where all worldwide researchers are trying to make a deep learning model to be more explainable. Why this? Accuracy is high, but we need explanation. If you have a machine learning, deep learning model, and which is telling them down the line after 10 years, you may develop a cancer, but they are not giving the reason why it will happen, then what will happen? Will you accept this? So, especially in the healthcare or any sensitive matters where it might be powerful method to give the accurate result, but the explanation is required why it would be happened. It should not be like only the Jyotish that just predict without explanation. But the moment we add some explanation, it becomes so powerful and rational that everyone will accept it. So this is the one of the important issue, that to make this deep learning models to be explainable. Some last 1 or 2 years you may see that works are coming and researchers are taking time to make this deep learning to be more explainable in so many applications. Sometimes not needed, but in many applications we need to get explanation of the output, why it is happening. And it what happened in the curiosity of the human mind. Most of the time, if someone tell that, and if you are happy that okay, it is happening, okay, some benefit, you don't ask most of the time why. But something negative happened, always we ask why it is, why with me. We need explanation. Positive impact, we forget, okay, something positive, I'm getting a money somewhere, okay. But most of the time, if someone will take your money, then you will worried and ask why it is happening. Tell me why you will take this, what is the rationale behind that. So in many applications, this is very, very important. So well, quickly now I will talk about this moving ahead. So that I will talk about the transfer learning. And within that, this representation learning is very, very important part. But representation learning is basically the term coined. It's basically, it's somehow not exactly synonymous to the deep learning, but it was coined like that. What is the idea of this representation learning? Is that we have a data set. And let I will connect through the linear algebra part. The basis examples. What happens if in the space, in the three-dimensional space, if you know that in a three-dimensional space, you need a three independent vectors. Three-dimensional space may have the infinite points, but you need only three independent three-dimensional vectors. If it is there and if you are able to get it, then any vector, any point on that space, you can represent using the combination of those three vectors. I'm talking about the three dimension. So in a three dimension, if we have the basis vector, basis means the three independent vectors which span the whole space, then in that case, we have a representation, three vectors only, which can, using those three vectors, I can get all any points you just give me, I will represent through that. The same, not exactly, you can borrow that idea as a representation. If you have an image, you think about if you have an image, and what we do in the image processing and all, can I represent the image? Image is basically, let's talk about the matrix. So can we represent a matrix of images like this, such a way so that with the combination of that representation, any image you just give me and I will recombine. So basically representation learning, what we talk about in the transfer learning role, I will discuss in the coming slide. We look at to represent a data. Why this? What happened in the feature engineering in machine learning? We collect a feature. Who will tell me if there is an image of car, what should be the feature to represent the car? Someone can say, oh, color. Which color is sufficient feature to represent, to know that is it a car or not? No. The same color may have anything. Then what should be the feature in that car? Okay, four wheel. Okay, let four wheel. But if you take a capture an image, very rare that on the four wheel you can capture. Then what should be their feature in a car to say that okay, it's a car? So what kind of pattern is needed to get that? Okay, my classifier will tell me it's a car. Human mind does it. If you show your kids 4 or 5 times car, he or she will be able to recognize that it's a car. But I want to make a model to robot to teach it, it becomes very difficult. So that representation of features, how we do that, so that our learning model, our learning could be much easier and fast, and model will perform better. So this is the representation, which is very, very important. People have done a lot of work to develop the representation for the languages. If you talk about the English, you talk about the Hindi, there are some letter and a lot of, if you go and read the history, then A, B, C, D, if I talk about, or Ka, Kha, Ga, Gha, if I will talk about the Hindi, then people have this developed this structure, representation, then top of that, they build up the word, then top of that, they will develop the sentence and paragraph, whole story writing. This is the representation, a small representation, and then they are able to capture the whole sentence and story we can write using that. So representations are very, very important everywhere. Same way representation for machine learning or deep learning models are very, very important. How to represent the features, what should be there in the feature, who will tell me? And that's how, what happened in the deep learning and other. In the deep learning, it's effective way to learn representation of data. And if you, those who are working in the deep learning, you just see that. The structure of the learning, people say that in the hidden node or CNN, dimension, what should be the size. This one is not sufficient. One structure of a deep learning structure is not sufficient for each and every problem which you are solving. So what we do in generally as a layman, problems, and then if you are going to apply deep learning, you just simulate a different permutation combination of the structure, and then you say that okay, performance learning is happening. Getting that structure for a particular data, that's what the representation of that data set, such a way that the learning is happening better. So the representation learning means that structured learning, you can say that, or architecture of this deep learning model. What should be that architecture and how we learn that? And if there are a formula so that for any problem I will put it and I will get an architecture? Not yet. Empirically you have to do and then learn that. So this representation learning is very, very important. Apart from other things, deep learning is giving a lot of success in that application of representation learning, and you can see that. So in every representation learning task, what we do that earlier in the machine learning part, we have a raw data, we do the cleaning data, we took the features, then we develop the model. Then later on, it could be a supervised, unsupervised, and we develop that. So this is what representation learning, how to represent the feature. I have a data set only. So how to represent all the features so that the model performs. Learning could happen in better way. So this is the important part, and how we do that, how we get this the best one, how this architecture, and that's why in the deep learning we talk about too much about the architecture. There are certain properties which should be there in any presentation learning, but though I will not go into too much on that. It should be smooth, multiple. Okay, that's right. I don't want to give on that. Okay, because more focus towards the transfer learning. So many kind of algorithms now work around, researchers are doing work in that. It's a deep learning, the buzzword nowadays. And there are probabilistic model also. It could be a probabilistic graphical models. It could be a Bayesian network. It could be a Markov random field, or many other kind of things you can see that. And it could be a learning as a manifold learning or representational learning for transfer learning. So in this talk more, I will talk about representational learning for transfer learning. Okay. So once you go in the deep learning taxonomy, you may see that the many different algorithms which are, okay, let it be. I will talk about the transfer learning. What happened in the transfer learning and why this transfer learning is needed? Think about that, how it is inspired from the human being. As a human being, what happened? If I know that any programming language for sake of simplicity, if I know the C and how to write a program, then quickly I can adopt my skill very fast way in the any Python or any other languages. So as a human, what happened? We are adaptive and we transfer our knowledge from one task to other task quickly. If the task is similar to the previous task, then much faster way. If somehow little similarity is less, then okay, it becomes difficult for human also, but human have that capability to use that knowledge, whatever he or she have in the new task, if we had some experience of that kind of problem. Well, so can we develop a machine learning model where knowledge we can transfer from one task or one domain, one data set to other domain, other data sets? And how we can do that? What are the different scenarios? So especially after 2006 and nowadays, you can see that most of the time people are working transfer learning, huge application every day coming, and many people are using this image net trained models for their own data sets to play with that, because they cannot. Google and Facebook have trained huge big network model which you can use for your data sets also. This is one of the success of transfer learning. You can see that within that transfer learning, many challenging problems are. Few of them I will introduce in the coming slides. So this transfer learning, the whole idea is basically that sharing the knowledge. One way in the machine learning task is that I have 100 data, and after 10 days again 100 data comes out. So one way is that now I have trained a model on 100 data. It came again 100 data, then either you make 100 and 100, 200 data sets, and again you learn the algorithm on 200 data sets. From 200 to 300, so again total 300, again you relearn your algorithm on 300 data sets. So data sets are increasing. One thing what we can do that, okay, just increase your data sets and again relearn the whole model on these data sets. So in that way, we are not transferring any knowledge. I'm talking about the 100. So you can say, okay, 100, 200, 300, what is that problem? Just do that. But at the same time, if it is a billion data, and then you are doing, we have a 1 billion data and 5 data comes out. Again, relearn and 1 billion 5 data and again doing that. Okay, why the time we are consuming, wasting. So sometimes we have to adopt quickly rather than going from the scratch and learn the whole parameters of the model. It will be better to adopt than how we can, so that it have only the positive impact. But in the process, when we can do that transfer and when we cannot do that transfer. So in that scenario, how we can share, and within that category, many kind of different kind of problems will be. So the whole idea of MLDL model, machine learning model, is traditionally what we do if data set and model is there, we do that. This is the triangle, and we do that learning and relearning. Another one, data set is different, model may be different, and then we do that classification. But the whole idea is in this transfer learning is how to share the knowledge, how the things have been done in the past may be used for the new task or new data, rather than going on the whole data and again doing the learning, how we can do that. Some question was there, maybe I will see. Okay, last I will see. Or you can unmute and ask, otherwise last I will see. Okay, so in general, transfer learning involves the following two tasks: to identify the commonality between task and domain. Is it anything common? Task is common, or domain is same and task is changing, or just exactly means the knowledge of programming, and then you are saying that the knowledge in history. It may not be that kind of transfer, may not be. But only that your skill and analytical skill may help, but that knowledge may not be shared. To transfer the knowledge, one to identify that how much it is common, and then if it is some way, then how and what needs to be transferred from one task or one domain to other one. And it is basically helpful in a scenario where few kind of label data sets are available. Sometimes that I'm going to discuss. What I said, that either satellite or many other different applications where unlabeled data sets are more and labeled data sets are very, very less. Then in that case, this transfer learning may be a way to achieve a better result. So why transfer learning? Data sets unavailable, expensive to procure, and especially doing the labeling is very difficult. And sometimes theoretical test data is different from the real world data. So theoretical data sets the model develops. So how it could be adopted for the real life data sets. So some fine tuning and adopt somehow we can do that. And then each client has individual preferences. That's the okay. That example I will tell you through one example how it could be adaptive model for each user. One handwriting example I will discuss that. So mathematically, I will not take on that, but mathematically how to represent that this transfer learning model. In that case, we have a data set. We categorize that the two components in that any data sets X and corresponding Px means distribution is known. What is that? It can be a source domain, two data sets. I can say that. One I can say where the huge data sets are in the source domain, another one I can say target. What it means, I have some learning in this source data set and I want to transfer the learning to the target data. So target data is where we are going to transfer the knowledge. Source is there, the data set is, our source domain is where we are doing some learning, but that learning we are going to use as a source for the other target where we are going to transfer the knowledge. Okay, so these two things you just understand. And in a source domain also there is a task. So in the source domain, you have X data sets and their task in the source domain. And then a target domain also have a data sets and some certain task in the domain. So you want to transfer from the source domain to target domain. So this is the representation for us data sets. And what is the transfer learning basically is that given a source domain with corresponding source task, so source is there, task is there, and a target domain. So from the so S is representing basically that source and this T is representing the target. So transfer learning is the process of improving the target predictive function, target predictive performance, target learning performance by using the related information from DS and TS, where DS means data sets in the source domain not equal to data sets in the target domain, and or many combinations are possible. Many combinations of this is possible. Target domain not equal to data. So it may be or it may not be. So any 4 combination will make it in a transfer learning scenario. Transfer learning, what can get transferred? One thing is that instances. Suppose in the source domain you have a billion data and target domain only 50 data. One thing is that you know that any algorithm you apply with the 50 data accuracy will be somehow it will be poor. But as the data sets will increase, accuracy will be increased. But the scarcity of the training data in the target domain is one of the important part which we want to solve. So in that case, if we go with the transfer learning, what happened? One kind of transfer could be that instances. When some weighting criteria we can assign and some data or instance from the source we may transfer to the target looking at the similarity or some metric, okay, which one should be transferred. There are certain methods for that. Then another possibility could be the feature transfer. Some feature from the source we can transfer to the target domain. So we encode in such a way so that that feature could be used in the target domain. That part I will discuss in the coming slide. All things I'm not going to discuss, but 1 or 2 cases I will discuss. So one thing is the feature. So you learn some feature from that source domain and use that feature in the target domain and then see that performance are improving or not. Another is the parameter. What is the parameter? If you know the machine learning, what happened either in the support vector and or in any algorithm, there are certain parameters or weight vectors you can say of the NN or logistic regression, which we learned that. So one possibility could be whatever the weight value you learn in the source domain, can you use that in the target domain? This is one case, and that's what many fine-tuning of that model we do that. You can see it. Relational knowledge. So sometimes we just prototype relational matrix we measure and then see that which features are relational to a particular data target domain data set have a certain kind of relation, and then we borrow that feature or relations and that. So basically these 3 4s are important way to do this transfer learning, and based on that many algorithms or many processes have been developed. It's not only the unique researchers have developed many processes to achieve that. Well, in the transfer learning and this taxonomy, many different problems you will see that people are solving. It's not the unique problem, different set of problem you can see. Sorry. So I talked about the source and target domain. So we have 2 different, we want to learn in the source, we want to transfer to the target. How many different kind of problem we can create in this? One, source domain don't care means data sets may be label or not label. But in the target domain, data sets are label. This is known as inductive transfer learning. How to do that? How to solve this? Even there are different ways to do that. Okay. So inductive transfer learning where target domain is labeled, but source domain may be labeled or maybe not be labeled. It's a no. Transductive where source domain is labeled but target domain is unlabeled. We have just the data, but it's unlabeled. So how we do that? It's a transductive. So transductive is a little bit more. Okay, something level you have learned, but where you are going to transfer, don't know. There is no label. So how you can transfer? Because target is not known, and something targeted work you did it, but how this knowledge could be transferred? So this is known as the transductive scenario, where source domain is labeled but target domain is unlabeled. So just see the data. What kind of data sets are there? The source is target labeled or not, target is labeled or not, and that is covered in the model. And if source and target, the most difficult challenging is both are unlabeled, then how we can transfer something you have learned? I don't know what I know that. And some problem is there, I don't know what there I have to do. But how then source and target both are unlabeled? How to solve this? This is the most challenging. When something abstract learning, you can say that where as a need comes out, we can apply. So it's very difficult to do perform without any targeted, but still this kind of problem you may think of is a scenario where the transfer learning could be possible, where target domain and source domain both are unlabeled. Within that inductive one, some I'm going to further because there are so many algorithms could be possible in a different scenario. Now within the inductive, the most famous you might have what the so inductive is where source and target domain is labeled, but source domain can be labeled or all non-labeled. Again, this category can be classified as two. If not available source domain and source domain is not targeted and not labeled and target domain is labeled, this is self-taught learning, which I'm going to discuss in detail, little detail with coming slide. The self-taught learning, where the source domain is unlabeled but target domain is labeled. Another category, multitasking, where the source and target both are labeled. This is the inductive transfer learning. Within that inductive, you can say that source domain have a label or unlabeled data, but the target is available. So either it's a multitask or it is a self-taught. So I will talk about the self-taught learning here. Okay, there are. Okay. So let's see one example. On this, within the self-taught learning, if you see that, just a minute. Within that self-taught learning, natural scenes are their image. And this is like the bigger picture is source domain. Here we are not saying that what a particular image is. It's a self-taught means the source domain is unlabeled. So no label or no tagging. What is there in this image? It's a building or high-rise building or sunrise or sunset or walking people or beautiful valley or something. Just a scene. Natural scenes, but what inside there in that image you don't know. So this is the example. You can say the source domain is completely unlabeled. No labels are available. But there is a target domain. And in a target domain, only you have a two image. Only two image. Like you want to classify that there is a two image, one image of car, one image of bike, and then you let's forget about the source domain now. Only two images you want to classify because its labels are available. This is a motorcycle, this is car, and a new new image is coming, and you have to tell that what is this? Is it a car or not car? Then what happened? Only two images, And if I ask that, do it. So performance, just forget the source domain. Any algorithm you apply on that, the performance will be poor. The moment the image of car in the training data sets in the target domain, you will increase, then of course accuracy of this model will increase. So either you increase this data set huge way so that learning model no need to transfer anything from anywhere. But in a scenario where not possible to increase that level information, and very few, either one available or two levels, one sort, few sorts, so many algorithms nowadays are coming. So how we can transfer the knowledge? And this could be a different kind of problem. I'm talking about the transferring the knowledge from a source where data sets are available. The same problem you can model it, transferring the model from the label data, means multitasking also you can. So in the source domain, how we can transfer the knowledge from this task to this? And especially this Brother Traina and all this, they did in 2007 or 8, the first problem. So first time what they did it, that they tried to solve 8 or 9. Yes, probably around 10. Just see it. Basically, they use it, the basis vector, what you used to see in the linear algebra. First time they used that part. Later on, many variations comes out and autoencoder comes out in the place, which I will talk. So the idea is to learn some feature from here. And then feed that feature, where there are many ways to do the transfer learning. And one is the feature sharing. So I will talk about the feature sharing. Data sets which are unlabeled, we have to learn some feature which I can transfer to the new task domain, target domain, and which I will see that which is supporting for the case of improving the knowledge or improving the accuracy or not. So for that, one of the famous way of doing is that for unlabeled data, and if you want to do the feature engineering and learning the important features, okay, this PCA and all is one of the important part. You can do that. Through that also you can learn. But the more deeper and better non-linear feature extraction learning way is doing the autoencoder. So even in the 2-3 years before in my lab, student did it. We placed the autoencoder to learn the features in this place. And then once you learn the feature, non-linear feature from this place, use that feature to the transfer that feature in this case and do this classification in the target domain. Okay. So what happened in the autoencoder, instead of too much maths, the idea of autoencoder later I will talk about. Idea of autoencoder is to learn. We talk about the source domain first. So in the source domain, what happened? We apply autoencoder in this place. What autoencoder does? Okay, from mathematics will come up. You take any input here, any image, and reproduce the same image because you don't have the label for that image. So what you do? Only one image is there. So my face is there. What I will do? Will put my face. I will give to the input to the network. I will do some representation of that network. Okay, some representation as a hidden layer. And then from the same representation, again, I will try to reproduce my face. So the input is X and output is X cap. Or it could be exactly X. Our whole idea is to make this X. So what happened in the autoencoder, we took the input, we encode in such a way so that from this encoding, this vector, this feature, you can say that representation of this encoding, we are able to again relearn using another kind of network, you can say, the same image. If we are able to do so, in the bargain of that, what we achieve, You can say that same face you give, take the output. Why to learn this? How will you ensure that this learning is happening? And if it is so, even though learning is happening, what is the fun in that? The whole idea is that if you have a source domain, huge number of image, and the same network encoder, decoder, model, autoencoder, if you are placing in that, which for every image you give, they are able to learn a hidden layer, this representation such that if you are able to reproduce all the images, it means this representation, hidden edge, have a power to reproduce all the images. Okay. So in the bargain of that, we want to learn this encoding and decoding from a source domain data sets which are unlabeled. So the whole idea is the distance between x as an input and x cap should be minimum. Means the distance of, and that's why this equation I'm going to the reverse engineering. The whole idea is minimize x norm between x and x cap. Actual input and output, this distance should be minimum. So you can use this norm. So it could be Euclidean. In between what is happening, through this, we are learning one representation. You can say this is H, and then you are saying F. So H is encoding this, and then from H you are decoding this. So that's why the function is H1 is encoding, and then you encode the input such a way then and decode that, and then whatever the decoding comes out, this X and X cap should be minimum, and that's what the transfer autoencoder is. Autoencoder, what it does, generally in between we encode in such a way so that we can decode again, and in the bargain of that we learn a feature representation such that it could be used for many images. So what happened then? In the source domain, which have many huge number of data sets, can be imagined. And if you have a representation for that, feature representation, then okay, very nice. Then once you learn this autoencoder decoder, what you do, how to transfer in the target domain? You cut it down this, remove this decoder part from your network. Pass only the encoder part to your target domain. We have a source domain, we have a target domain. So what is the idea in the source and target domain? Is to pass the source domain. Encoding means something we are representing here. We are able to, each image we are representing in here. And then decoding is we are reproducing. So once the training happened in there, okay, discard this decoding part. Now, what we are saying that for every image we have one representation which is very nicely representing all features. That encoding part will be passed to the target domain which have the very, very less data. And then the target domain data sets will be encoded through this encoder, not decoder. Your target data sets will be passed to this. The feature of that will be learned through this. And then your classifier now will be applied on those encoded data sets only. So the feature in what happened, feature has been transferred from the source domain to the target domain. Through this encoding, the representation of target domain feature will be done. And this experiment was done, and then what observation was, even this, just see that in a different features, how many features you are passing. In this case, you just see that this is SVM into 100, so 100 or 200 images like that, even in the MNIST data sets. Even 100 data sets or 500 data sets, just see that, okay. The baseline model in case of 100 or 200, the accuracy is 50 to 60%. And something if you are transferring, let you are transferring from the scene, not sure that it's unlabeled data. If it has been a labeled data, story might be different. even though in that case this was done, and what was the observation that the moment this using this the transfer learning happened, you see that the accuracy is better compared to this. Of course, if the data set will increase in the target domain, accuracy of the model will increase. But the real challenge is that this kind of models we want to apply where the target domain have a less number of data sets. And in that case, what we are seeing that, okay, this is the self-taught learning only domain where the scene knowledge, scene images, you are transferring to the MNIST data sets where the numbers are there. But still in this case, some positive support of the transfer was observed. So what we are saying that something has been learned in a source domain now can be transferred to the target domain. Same way, this is the within that a different application and different feature representation obtained from deep autoencoder. Either you again, I'm not going in that too much, and the autoencoder with a single hidden layer encoding or multiple hidden layer, and you just see that if you the power of encoding will increase, it may support to the positive to increase the accuracy, but that part we need to further discuss what variety of autoencoder you can play. I'm not going later on also so in the continuous of that, but the plain autoencoder or convolution autoencoder, which autoencoder, what I said that learning the feature, encoding and decoding. So for the encoding, are you going to use only the hidden layer, increasing the depth in encoding and decoding part, or you can use convolution autoencoder, or variety of different autoencoders are available. And accordingly, you can see that, okay, how it is supporting to the argument that accuracy is increasing or not. So I will not go in detail looking at the time, but yes, it's you're in this green part encoding and then decoding. So there are a variety of things you can do to transfer the feature. To first in the source domain, learn the better representation. As your representation and learn encoding will be better, of course, then whenever you transfer, it may support more positively compared to the other one. So the same experiment with the lesser data, and it was different data sets, more challenging data set. And observation was that this transfer of knowledge is supporting very nicely in this case also. Okay. So this is one application of self-taught learning and transfer learning. There are so many scenarios, so I could not cover. Is there any difference between unsupervised and, can you repeat question? Okay. Difference in that in unsupervised learning, in the source domain, it's unsupervised. But in the self-taught, the name is there. The problem is that we are doing the transfer learning. In a source, we are doing the unsupervised basically, and the target have some label. So this is self-taught, the name was given, coined by the Andrew and team. The idea is this category of problem where source domain is unlabeled and target domain is labeled. Okay. Only what unsupervised learning, where we are not talking about the transfer learning part. But in the self-taught, we are talking about the transfer of knowledge. That's what you can understand. Because in the source domain, we are doing the unsupervised autoencoder or PCA. You may think about that. We are doing the unsupervised, and then we learn the features, and then we transfer in a target domain where we have some level data, and then we are using. Okay, someone have asked that whether data representation is same that of data preparation before applying data learning. Please explain. No. Preparation may be sometimes times of, you can say, missing data and something you are going to put on some normalization if you are doing that, some scaling you are doing the data. But representation means in a data sets, what is the best way of feature extraction or some representation? If you are putting a data, you don't know which data will support or not. 10 feature, 2000 feature, 200 feature. So representation learning means, so within that raw data, if we talk about the architecture, what is happening in that architecture in feature engineering learning? So how to represent in the best way, not necessarily that if the raw data you put in your any deep learning or ML model, then the learning will be better. So the architecture is what happened in the any deep learning architecture. We say that deep learning architecture is also a representation. How, what should be the feature combination permutation so that the accuracy of the model will increase. So raw data is the only part in the input. So from within the input, how these features could be combined or inclined, extracted, so that the performance of the model will increase. So that's what the difference in that way. Okay, some other question, how we use presentation learning. Okay, I'm coming. One or two things how to use it. That way quickly in the next 15 minutes I will talk about the application domain only. It's a huge application in NLP. You can see that, and especially if I talk about the natural language processing, many way natural language or performance are named entity recognition or many different domain. You can see that type of transfer learning in NLP. It could be a sequential transfer learning. Again, transfer learning can categorize in the transductive and inductive, what I discussed there. And in that, it could be a multitasking, cross-lingual learning. Something, suppose you the problem is that one model you have tuned from Hindi to Marathi or Hindi to English, how I can use the same? Will it be possible to that language transfer model to be adaptive, make adaptive from Hindi to English to Marathi or Marathi to Hindi? If yes, then how we can? The one thing is that the data sets. What is happening if you, I will talk about the Indian scenario. We have a central language nowadays, the English to Hindi or English to Marathi or English to Bengali or English to Kannada, anyone you can. But if I talk about the data sets, give me a data set so that I can make a language model from Hindi to Marathi or Hindi to Punjabi. Nowadays, the data sets are less, or we have to make that. So either you develop, this is the important part, and that's why many huge applications are possible in the Indian scenario, making language transformation tool. And down the line, it is coming. Many things, startups and industry are working. Maybe it is there. So very soon, what will happen? Many language translations are coming, and they might be using in the background some kind of transfer learning also. Now, nowadays, no language barrier. We would have an app. I will speak in Hindi. I will be in the Maharashtra, and where the people are left, for example, Maharashtra, randomly I have picked. A person in the village is speaking Marathi. If we could develop, just think about. Then you just open the app. He will speak Marathi, and something like written language comes out. You speak in Hindi, and then there will be a translator that will be converted Marathi to Hindi, and then you speak in Hindi, and then it will be translated to the Marathi. So the two person, without learning that through this system, they make communicate. And it's the worldwide nowadays to make this tourism more progress. In many industry and many countries have developed that. In India also, not so much, but people have started to make up the data set so that we can make a language translation model where each one, for every language, just think about if down the line there's IT application where people can go and speak one language. Okay, no need to be worried. Have an app, speak, and that model will help me to understand. So the language in NLP, it's a huge applications you can see in that way. So that also you may model somewhere some data sets, very less data sets are there in one domain, and when some other domain huge data sets. So how we can transfer the knowledge? Will it be helpful or not? Especially in that what is happening that for the English people have developed a lot of things, word to wake and the huge database they have developed. And we have to develop our own such kind of representation representation dictionary so that it can be used more robust model as a central, that it may say that one language, Indian language as a central, another language can be transferred according to that. So many people who are working at that, but still we need scope. So what is happening in that sequential transfer learning? Let's one or two quick I will do. Pre-training, and then we convert. There are many word to make to grow many pre-training language. We convert to the vector, and then we do the adoption, classification, labeling, question answering, anywhere, and we do that. This pre-training is very word to wake or something, BERT and some models. These models are trained, but most of the data sets where these models are trained are basically mostly trained on the English, but it needs to be because to capture the language, each language have their own semantics. And whatever the representation word to wake for the English may not be suitable exactly for the Hindi sentences and all. If you do directly, then Google Translator and then English and then do that. But in that scenario, the semantics of the Hindi or any other language may not be captured beautifully. So one challenge is there, but if not till now, then translate Hindi to English, then you do the word to wake, which you can fine tune according to your language, and then this fine tuning is what through transfer learning we do. Okay, one or two, instead of going in detail each and every term, you can see that the sentiment analysis, paraphrasing, question answering, dialogue, summarization, a huge application of that. How to do this transfer learning here? When I have a slide, I want to discuss that part rather than all the details. Sorry, I have put it all, but time. How to use to adopt period and model? Someone have asked, so that I will discuss. One way is that what people are doing. You just use the pre-trained model if data sets are available, and use that architecture for your own case. Bring that architecture as well as bring that parameters tuned up for their bigger data sets. And what you do then, I have this slide, I think. Yes. Something had been pre-trained, language model was pre-trained with their huge data sets, but you want to use that pre-trained model for your own data. Then what happened in the during pre-training, last layer is the target, and they have a task, and they have a different task, and you might have a less data sets and a particular task. Then what you can do, remove their task, but keep all the pre-trained model as well as their parameters value. Here you add your own task, remove that, add your task, and for your own data sets again, either exactly put a task, don't modify these weight parameters, and do the classification. This is the simplest way. But here, just you are removing the task from the pre-trained model, and the same training you are saying that, okay, it could be helpful in my task also, and you can develop here your task and do that. But most of the time it may not support if your data sets are not matching to this pre-trained model. Then what you do? In that case, what? Because that pre-trained model was trained with a huge number of parameters and huge number of data sets. So you cannot use all the make free all the parameters retuning for your own case. So as a layman, what you can say, okay, I will put the data sets and I can free some layer. One layer only. Free means those layer I will learn from my data, and other I can, this is unfreeze, and other I will freeze it. Okay, I think it is one slide I have put it. Okay, but not here. So one way is that task will be changed, and you can say this first layer level parameters will be unfreeze. Unfreeze means it will be tuned for your data sets. Remaining will be freeze. It means that the value will not, this weight value will not change using the back propagation or learning. Only the first layer parameters will be tuned up for your data sets. Bring the architecture, that pre-trained model, either you use the same parameters for your own architecture and then as a starting point and learn all the parameters, Or you can say only some parameters of the architecture I will learn from our own data, other parameter of the architecture I will use from the previous. So there are many permutations and combinations as a layman which you can use as a transfer learning or adaptive modeling for your own data sets where you can play that. So even in the NLP, because the one thing is that the data sets, either you have a huge data, then huge computing power, then you go and train your model from the scratch, or you can fine tune for your specific data using the some parameters to be unfreezed, and you can play with that and it will help you. Okay, each and every detail I will not go. So there are many applications which you can think about where you can use this open problems and feature direction in that, either okay, might be you are not knowing this meta learning and not phenomena, so I may not go that. So this is one of the problem is continuous learning, and challenging part is that make a model transfer learning so that if new data set comes, each time it should be adaptive from one task to other task to other task. So how continuously we can make a learning algorithm which can be adaptive, learning very well, and then the performance of that will improve. So nowadays, people are now the cutting edge research is that lifelong learning, making a model which will be adaptive. Lifelong means creative, adaptive, and doing the task very well. Okay, leave it. So some huge applications you can see there. Quickly, one or two. Also, only the application part I will share now. I will take 5 minutes more to discuss some problems in the vision also. In the transfer learning, I'm talking about now the open problems where you may open problem in the sense some work have been done in last 2-3 years, and you may see also. Not in the transfer learning challenging part is that if the target domain have only description, no image, the vision, and how you can that. This is the geo-sort learning. In the target domain, no image, only the description. Then how you can say that? Just transfer the knowledge. This is the one of the challenging problem, not so easy problem. Or if you have only one image in the target domain, then how you can increase the accuracy? This is the one-shot learning. If you have only one or two image, then two-shot learning or few-shot learning. So if in the target domain, very less labeled data sets, that's the challenging part. Real life problems where labeled data are very less, either one or two. And in the source domain, we have the huge number of past pre-trained or trained models. Then how I can do this learning where only one or two or no labeled data sets in the target domain? This is a very challenging problem, and what a huge applications in the state of the art. You may Google it and see that this zero-shot and few-shot applications in the vision and in many different applications of that. Even for the image captioning and all, you can see the transfer learning and all. Something you pre-trained model, then any new image comes out, how it can be transferred means something. So you can say that image of sport you have fine-tuned, or cricket you can, and then the same captioning, if you are using image captioning for some other kind of data, then how the fine-tuning and the transfer of knowledge is possible. So that application also, you can see that image generation from the scene graph. Okay, this is the one of the challenging problem. The scene graphs means some text and this orders are there, and how to generate the image. Or the future application is that if you can think about it, making an image and video. So many applications in creative art. You can see in the creative art how this transfer learning can be helpful to make a model. But the human brain is more adaptive, but making such model to work in even the constant domain is slightly difficult. But those who are interested may Google it and see that, and may take up that challenging domain where the transfer learning, how it could be helpful. Transfer learning is not the only solution, but it may be a supportive solution, what I can say, which you can use in a different problem. Even for mathematical expression, this is that. Write something and it should be converted in the doc or latex format. Not so easy. And because each user have a different writing style, So someone is writing in a different way. Can we make a system which can just give me image and I will convert it in the, so how this is one challenging problem without transfer learning also. But from one user to other user, data set will be increased. So how this transfer learning can be used, and how this accuracy of transformation from handwritten expression to the digital form can be possible, and accuracy can be improved using the transfer learning or incremental learning also. Incremental learning or something is also the part of that. So within that, now people are talking about the lifelong learning. What, as the data sets will increase, new kind of things comes out, experience increase, how this performance will improve with the time and with the data set. These are the different problems which you can think about. Data fusion techniques and transfer learning, where so many applications. It's not so many applications of this transfer learning in medical, to the health data, to the medical domain, or satellite, or in the wireless sensor where the machine learning and all you are using, or in any the image conversion, image captioning, mathematical expression, where you feel that this is the problem, where the challenge is that the data sets have the limited number of level something. So how incrementally we can learn, how the knowledge from one stage of learning from other stage we can use. If it is the scenario, then you may think about to develop your model as a transfer learning case, and then gradually you can improve your model. One thing is that if every data sets are available, all possible future data, then no, why transfer? I have a huge data and huge machine which can learn everything, then okay. But it is not going to happen. So how within the limitation and constraint we can perform the learning and improve the learning using the transfer learning, which you may explore in a different domain. So with this, I would like to stop here. Thank you all for listening. And if you have a question, I'll be happy to respond.